Hi, welcome to your lesson on solving exponential equations. Okay, let's begin here. Let's say you're given this equation, which is an exponential equation, because we can see the exponents are where the variables lie, and you were told to solve that. Okay, in this case, we've looked at ones like this. We noticed that the bases are somehow related. Maybe they can be written in the same as the same base, right? So the way we looked at that one was, well, this is 4 to the x, but this 16 can be rewritten as 4 squared. So all of a sudden we have the same base. Once we have the same base, things are easy. All right, so we have 4 squared and then x minus 3. So you multiply that through 2x minus 6, and now we know 4 to x power equals 4 to this power, so those two exponents must be equal to one another. So x equals that, because that's the only way these two sides will actually be equal to each other. So solve that, and we get an x value of 6. And that should work out here. 4 to the 6th power equals 16 to the 3rd power. It should work out. You can check. Okay, so those are easy when we can make the bases the same. What happens when we cannot? For example, in this one, there's no way to make that have a common base. Obviously, a 4 here, a 9 here. This could be 2 squared, of course. This could be 3 squared. But still, those bases are not the same. So in this case, we're going to use logs. And this is one of the main reasons that logs were discovered, I guess. I guess they were discovered, or were they created? Anyway, they were created or discovered for this purpose. Let's take a look. So we're going to use a change to log form first. 4 to the x power equals 9 can be changed to log of base 4 of 9 equals the exponent, which is x. Now we have log form. Now this, we have just learned in a recent video, the change of base formula. So why don't we use the change of base here? And the reason is only because sometimes it's easier to deal with a base other than 4, right? A base of 10, for example, is easy to deal with or easy to punch in your calculator. But if you do have a calculator that can change bases, like you can put a 4 as your base, then calculating this is easy, right? You can do that. But let's try through the change of base. When we do change of base on that, we can write log of 9 over log of 4, right? This number over this number. And log means here log of base 10, log base 10. So I changed the base from 4 to 10. This can easily be calculated now. Punch that in your calculator, and you get 1.58. Okay, so using logs and change of base allowed us to find an answer, even though we could not make common bases like here. Let's look at the same one by applying logs to both sides. So now we're going to do the approach which we also saw recently. You can actually put log of that equals log of that. Doing that is perfectly fine, because just like if we did +2 on each side or times 5 on each side, whatever we do with one side of an equation, as long as we do it to the other, their balance remains. So in this case, all we did is apply the log on this side and we applied a log on this side. So this is still a true equation. So now that we have that, we can solve for x by dropping the x in front here and then dividing by log of 4 to get x. So x equals log of 9 over log of 4. Notice that is exactly what we just had a moment ago when we did the change of base approach. So by applying log on both sides, it's the same thing as going through the process of changing to log form and then doing change of base. It's the same thing, all right? Now, that, of course, will give us the same answer. So now, never forget this technique. The idea of applying log on both sides is the standard technique for solving for an exponent that is a variable. All right, so apply log on both sides. And we're going to do some problems in this lesson on that. They will get a little tougher than this, but let's keep going. So how about this first one here? Use the technique we just looked at to solve this one. Okay, let's check. So that you can apply log on both sides, like we said. Drop the x down, divide by that log of 2, and you get this if you punch it in your calculator. Again, a log of 10 was used, log base 10 was used, as that is a simple one to punch in your calculator. Of course, if you want to think of that one as the other technique, you could take this, change it to this log equation here. Log base 2 of 10 equals x, and then you can go ahead and solve by change of base. So again, we get to the same place here by taking those steps as we have here. Okay, next one. Okay, that one, when we solve it, again, put log on both sides. In this case, in this example, they decided to put a natural log on each side, which is just fine. You can use any log you want. And just like we have a log base 10 or log button on our calculator, we also have a natural log button. So this is just as easy as using log base 10. So natural log on both sides, drop the 2x in front, divide by ln3, natural log of 3, and then divide by 2 as well. That's like this half here. And that's the answer for x. So there's our value here. Maybe before I reveal the solution, you tried using log base 10, and hopefully by the end you got to the same answer. It should be. That one, of course, again, if you decide to go from this step and do definition of a logarithm, we could do log base 3 of 20 equals 2x. And then 2x equals that, and you notice, again, we're at the same step here. In this case, I used log base 10 here when I did change of base instead of natural log, but again, it means the exact same thing. When you have that here, it will give you the same result as that. Okay, last one here. In this case, we apply the log to both sides, drop the 1 minus 2x in front here. Make sure that's in parentheses so we clearly see that is the multiplier for the entire log. Then we can divide by log of 5 equals that. Then the 1 has been subtracted. Then we have divided by negative 2, so there's a negative half in front here. Notice how these values, this has been kept as log, log, log all the way through, because you'll be more accurate in your answer if you don't calculate along the way. If you calculate along the way, you'll get decimal values, and there'll be rounding, and things will change. But if you keep it exactly as is until the very end, until this step, and punch that in your calculator, then you'll have a more precise answer. And once again, with that one, you could have begun by taking this, saying we have a log base 5 of 50 equals the exponent 1 minus 2x. That, again, will bring you to the same place as this did. We have this. I did a change of base on this, log of 50 over log of 5, and notice we're basically in the same place as we were here. All right, so with that, you're ready for an applied problem. It's always good to see how logs can be used for something real, a real application of logs. So take a look at this question and see if you can answer A. In A, we can say the radius of this, what is it, of the fungus on the tree at 0. So we put 0 in this equation because it says when it was first observed. So again, when something is first observed, we say the time equals 0, because this is time in days. And then, so time is 0 means right in the beginning. So time goes 0 here, we put 0 exponent, that means it becomes 5, because this becomes 2.4 to the 0, which is just 1. So we get 5. All right, how about question B? After 4 days, the radius is 8. Find the value of k. So it says after 4 days, the radius is 8. Okay, so you set up this equation here. 8 is your radius, so you replace the radius here with 8. You put in t equals 4. That t is replaced with a 4 for 4 days. K remains unknown, and we have everything else. Simplify some things. We can divide by 5 to get this, and then we can get to the steps where we use logs, right? We have an exponent that needs to be solved, therefore logs is the answer. So we do log on this side, drop the 4k in front, divide by this on this side, and we have it there, and also divide by 4, so that's what the 1/4 is here. That will give you this k value, and it's been rounded here. There's 3 significant figures. Okay, so make sure you really know this process. This is not difficult algebra. Once you see the process, it should be okay, but make sure you're able to get to that answer, and particularly, it's these kinds of problems you should be able to solve using logs like this. These applied problems are key. Okay, try C. In C, we're trying to get the fungus to get to a radius of 10, and we're seeing how long it will take. So now we know the k value. The k, it says, does it say that? No, it doesn't say that. Oh yeah, k is like a constant in this equation. So we kept the k value in there. Time is our variable, the one where we put in 1 day, 2 days, 3 days. So we leave the constant of 0.134, and then our unknown there remains the t in this case. All right, so we're going to divide by 5 to get this. Then we're going to apply log on both sides, drop the exponent to the front, divide by the log over here, and also divide by that, and we get a t value of this. So that one might have been tricky because maybe you're wondering about the k there, but again, this is a very common kind of situation. We have an equation, the k is some constant which we can find using some data we have like we did here, and then you can now apply the formula with the constant known to solve other values. All right, how about these? These are a little bit different and a little bit more challenging for sure. This first one, we're going to use the same approach, but it is a little tougher. Let's see if you can do it. So in this case, we can begin by putting log on both sides. All right, you're stuck with the 2 and the 5. There's nothing you can do. They're going to be there. Then this, by the rules of logs or laws of logs, we can break this up into log of 2 plus log of 3 to the x. On this side, log of 5 plus log of 2 to the x. Now notice we have x here and x here. So whenever we're solving equations, the goal is to get the variable on one side, right? So let's get the x things on one side. Let's see what we can do. First, we'll drop the x in front for both of them. Oh, I didn't drop it. Sorry, I moved it over first. So I put this log here and this log on the same side by subtracting the log of 2 to the x. I move that log of 2 to that side. Now I have these x's on one side. I can drop the x in both. And now I've dropped the x in both, I can factor out the x. So x times, and in parentheses, those two things equals that. Hopefully you see the next step from there. And it is to divide this side by this whole thing. And again, notice until the very end, we kept all the logs in there. We didn't put any decimal values in. We just kept it as it is. So that divided by that, punch that in one step on your calculator to get the most precise answer, which is this. So I hope that went okay, or at least when you tried, you were able to kind of make some progress, but now you see how to deal with that when you have the multiple exponents. Let's look at B now. In B, you look at this equation, and it should look familiar. Look at it closely. I see 3 terms. I see a squared here. So what is this? All right, hopefully you answered that. Looks like a quadratic. So if it's a quadratic, we can deal with it like this. Check this out. We look at it like this. I put the 2 out here to make it more clear that it's a quadratic. And now that you have a quadratic, you can factor it, and it factors into this. If it's hard to see how this factors into this, let's take a look at another approach to this kind of question that's often done. We set the exponential thing here equal to another variable. It's often that we use the variable a. So I'm going to say a equals that. So now when I rewrite this equation, if a replaces e to the x, then that becomes a squared, and this becomes negative 3a. And that's what I have here. In that equation, it's a little more clear maybe that it's quadratic, and then maybe it's easier to factor that for you. So the factoring of that is a minus 1 times a minus 2. That's how that factors. So make sure you know your factoring as well. Now that we have that, we can see it's the same as what we had here, because a is e to the x. So if I go back and put e to the x back in there, I get that and that. When you solve a quadratic like that that's been factored, we set each term equal to 0. So e to the x minus 1 equals 0. When you solve that, it's e to the x equals 1. And if you set e to the x minus 2 equal to 0, then you get e to the x equals 2. Now there's 2 possible answers. Those are not solved for x yet, right? So this one you can change to log form, and it's log base e, which is natural log of 1 equals x. And this one, if you change it to log form, it's log base e, which is natural log of 2 equals x. So here's our 2 answers, ln1 and ln2. And ln1 is just 0, and ln2 can remain like that. So those are our answers for that one there. Definitely a little trickier, but again, once you see that quadratic form and you try some things out, I'm sure you can put all your log skills to use to solving that one. I'm going to leave you with some challenge problems. Our textbook seems to kind of end with this kind of problem as the most challenging in terms of the algebra to logs. But I have a couple more challenge problems for you, so let's try these out. So one looks like this. See if you can solve that one using that same kind of technique. And you have, again, you have multiple x's here and here. It's going to involve more algebra, right? Let's check your work. Check closely. See what happened there. You can do it. Next one, try this one. So again, same idea. We have 2 exponents. Both of them have x in them. Makes it a little tougher to solve. There's going to be more algebra. Let's see if you can do it. Here's the answers for that one. That one I don't think I calculated further, but that can be, of course, calculated to a final answer. And finally, I have one more. Now this one has e to the 3x and 5 to the 1 minus x. So how about this one? How would you deal with this one? And there's the work for that one. In this case, I decided to use natural log on both sides only because I have e here, which makes it a little easier to work with. One thing that happened here is this ln e here became 1. And of course, you may know it happened because of this. So take a look at what happened there, why this turned into a 1, and then proceed from there. So these last 3 were quick, but I expect you to pause and look at all the work and make sure you try those out. Great work.